The Earth's temperature has risen about 1 degree Celsius since humans started emitting planet-warming greenhouse gases to the atmosphere 150 years ago. However, most of this temperature change has occurred over the past few decades. In those last few decades, we've already been seeing the slew of negative consequences of those emissions on our global climate. The International Paris Agreement, enacted in 2016, has been the most significant global effort against climate change, where almost 200 countries made an agreement to try to keep global warming to below 1.5 degrees C compared to pre-industrial times. But we're more than 2/3 of the way to 1.5 C warming, and global greenhouse gas emissions are continuing to increase. As long as humans continue to burn fossil fuels, global temperatures will continue to rise. Even if we stopped emissions today, it would take centuries before atmospheric CO2 and temperature would really decrease due to natural climate system feedbacks. Because of the world's continued reliance on fossil fuels and the immense challenge of decarbonizing some technologies like air travel, the Intergovernmental Panel on Climate Change has recommended the use of carbon dioxide removal, or CDR, to mitigate climate change. The IPCC states that CDR is an important tool in case we temporarily overshoot the 1.5 C warming target. Okay, so what is CDR? And how useful can it actually be in our fight to solve climate change? My name is Lauren Barrett, and I'm a PhD candidate in oceanography, and I specialize in the carbon cycle. So let's talk about CDR. Carbon dioxide removal, or CDR, is a broad term for any technology that takes carbon dioxide out of the atmosphere and puts it in another place, usually in another form. Some CDR technology doesn't really seem like technology at all. In fact, planting trees is actually considered a CDR technique. Not all CDR relies on natural processes. In general, we can classify CDR into natural and engineered categories. Probably the most sci-fi looking form of CDR is direct air capture, or DAC. This involves pulling ambient air into a reaction vessel where carbon dioxide reacts with chemicals to form a solid compound. This carbonate solid is then heated up so that only the CO2 escapes, and it's then concentrated and transported elsewhere. The transported CO2 can either be recycled through use in industry, or it can be dissolved in water and then pumped into rock formations, where it will react into carbonates over time, and that is called carbon capture and storage, or CCS. Though it may seem like there's a lot of CO2 in the air because of how much it affects the climate, it's actually pretty dilute compared to the major gases that make up the air that we breathe. The CO2 concentration in air is only about 400 parts per million, or 0.04%. Though that concentration is significant with regards to climate change, it's still pretty hard to filter that out of the ambient air efficiently. All of that air filtering and especially heating up reagents to concentrate CO2 requires a lot of energy. Right now, direct air capture uses about 1,200 kilowatt hours of energy per ton of CO2 captured. For context, that's about how much energy the average household refrigerator uses in an entire year. Again, that's 1,200 kilowatt hours of energy for just 1 ton of CO2, and CDR technology is expected to take up billions of tons of CO2 in the coming decades. Direct air capture is currently pretty expensive, costing anywhere between $125 and $350 per ton of CO2 removed. Emerging research will probably bring that cost down in the coming years, but we're still years away from being able to apply DAC for reducing atmospheric CO2. However, if CCS is coupled with a renewable energy source like bioenergy, the resulting process, bioenergy with carbon capture and storage, or BECCS, can be a form of CDR that also produces energy. Right now, BECCS technology costs about $20 to $100 per ton of CO2 captured. There are also some concerns with the storage of CO2 in rock formations, since pipelines could leak, and the placement of these plants and the transported carbon could pose environmental justice concerns regarding energy use and the uncertainty of how permanent the storage techniques are, because we haven't been monitoring them for a long time. In my opinion, this next technology falls somewhere in between natural and engineered solutions. Ocean alkalinity enhancement, or its land-based analog enhanced weathering, are both CDR methods that accelerate the millennial timescale natural climate cycles that occur between alkaline rocks and the ocean. When water that contains CO2 reacts with alkaline rocks, it forms bicarbonate. Bicarbonate is a negatively charged ion that contributes to the alkalinity of water, or the ability of water to resist a change in pH when more acidity is added. In seawater, CO2 naturally equilibrates between carbonic acid, bicarbonate, and carbonate, but the higher the pH, the less proportion of CO2 there is in the water. This is the basis for enhanced weathering and ocean alkalinity enhancement. Take up CO2 by dissolving rocks, and keep the carbonate system equilibrium in water towards bicarbonate and carbonate so you can prevent CO2 release. In the case of enhanced weathering, alkaline rocks such as basalt or olivine are ground up and spread in areas that have naturally high weathering rates, so this can be on land or in coastal areas. In the case of ocean alkalinity enhancement, ground up rocks such as carbonates are directly added to the ocean's surface. It's currently unclear what impacts this change in water chemistry could have on aquatic and marine ecosystems, so this technology needs quite a bit more research. Right now, implementation of this technology costs about $100 to $200 per ton of CO2 removed. Now let's move on to what are considered the more natural CDR methods. Many natural solutions have co-benefits beyond just the removal of carbon dioxide, including air purification, habitat restoration, and many other ecosystem services. The most obvious natural CDR method is reforestation and afforestation, basically planting trees. Through the process of photosynthesis, trees naturally take up carbon dioxide and turn it into plant material. While reforestation involves planting trees on previously forested land, afforestation is planting trees where there wasn't previously a forest. The effectiveness of planting trees for removing carbon dioxide from the atmosphere depends on where and what kind of trees are planted. Reforestation can also be a less permanent solution based on the lifetime of the forest. While the other services provided by forests definitely have value, the cost specifically related to carbon uptake is about $50 per ton of carbon dioxide. Another form of natural CDR is called blue carbon, which relies on the storage of carbon in coastal wetlands or mangroves. If you've ever heard of blue carbon and wondered about it, it's just a term that describes carbon in the ocean. The carbon itself is not actually blue. This CDR technique comes from the fact that coastal wetlands are extremely productive environments, meaning that plants there transform a lot of CO2 into organic material and quickly bury it in sediments. Wetlands also produce methane though, and methane's a more powerful greenhouse gas than CO2, so this could end up countering the carbon dioxide removal efficiency. So in many cases, the carbon uptake capacity of coastal ecosystems is relatively modest on a global scale. Much like reforestation, wetland restoration has benefits aside from CO2 removal and can be seen as both mitigation and adaptation to climate change. Wetlands are important for water purification, protection from sea level rise, havens for migratory birds, and much more. So now that we're all familiar with the various technologies involved in carbon dioxide removal, how much of this are we going to have to do? Well, honestly, that depends on us as humans. The sooner our society divests from fossil fuels and reduces the output of CO2 emissions in the first place, the less of a burden we put on future generations to have to remove that CO2 from the atmosphere to stabilize the climate. There's also a good reason that billionaires and fossil fuel corporations are excited by and investing in CDR technology. It allows them to continue to commodify the environment. Some experts, including myself, are worried that the recent focus on CDR technology can be seen as an effort to deflect from the more urgent need to stop emitting greenhouse gases. CDR should not be seen as our primary tool for mitigating climate change, but rather an additional tool for dealing with our historical emissions. Carbon dioxide removal can be a powerful tool allowing humanity to turn back the clock on centuries of greenhouse gas emissions. However, it's important that we don't repeat the mistakes of our past and that we ensure that we understand the environmental impacts of CDR technologies before deploying them at a global scale. Thanks very much for watching, and I hope you learned something from this video. Comment below the most surprising thing that you learned and what your opinion is about the use of CDR technology. All of the sources that I referenced for this video are linked in the description, along with some other valuable reading. Peace!